So, dear students, in this lecture, as I told you in the last class, we have discussed, we will discuss about these two important factors. One is the existence of solution, and the second one is the uniqueness of the solution, right? So, about the uniqueness of the solution, right? So, if you now let us go to the existence of the theorem. So, let it be. So far, we have not discussed any theorem. So, let the theorem, this is called the existence theorem. Existence theorem, right? So, and then let us study that. Okay, existence theorem. So, what is your IEP? IEP is y dash is equal to f of x comma y, y of x not equal to y naught. Okay. So, let f of x comma y be continuous. At all points in the closed rectangular region R, which is x minus x naught is less than equal to a, y minus y naught is less than equal to b. So here, if you see that since f is continuous in continuous in the closed region R, so this implies a maximum of because you know that in a continuous function a closed domain is bounded, so the maximum of f exists, right? And in fact, so that means its maximum exists means f of x y mod is less than equal to m, where m is this maximum. Okay, so then, so I can put stuff here, and then the IVP has, if the function is continuous in a closed rectangular region R, then the IVP has at least, then the solution exists as at least one solution, at least. It may be more than one, but at least one solution I can tell. Okay, and the solution is defined at least for all x in the interval where it is exists, the solution in the interval I, which is equal to x minus x naught mod less than equal to h, where h is minimum of a comma e by m, where m is the maximum of x. So the proof you have already seen in your BSc, so just I will omit it here. Okay, the proof I will omit it. So what is the important thing is that if f is continuous, then at least one solution exists in this closed bounded domain, and the solution will exist in this interval. So this is the main point. Okay, so this is the main point. So let me go to the more details about this and few examples. Okay. So since since you have y dash is equal to f of x comma y, and f of x comma y is bounded and that is less than equal to m. This implies y dash mod is less than equal to m, and that means the slope of every solution. Y dash means derivative. Here derivative means slope. You know that every solution curve lies in the interval where minus m to m, right? By this property is mentioned. So here what we can conclude that, in fact we can take closed interval, there is no problem. So here the two cases, if h which is the minimum of a comma b by m equal to a, then the solution exists. Then the solution exists at least in the interval where, in the interval according to the theorem, in the interval x minus x naught is less than equal to a. That means x naught minus a to x naught plus a, right? Okay, so in the interval this. Now if your h, which is the minimum of a comma b by m equal to b by m, right? If it is b by m, then the solution exists. Then the solution exists at least in the interval x minus x naught is less than equal to b by m. That means in the interval x naught minus b by m to x naught plus b by m. Okay. So what so far we have seen that if you look towards this, so suppose you have a point x naught here and x naught minus a here, x naught plus a here, and then you have a point y naught here. You have y naught. Suppose this is your y-axis, so this is y naught plus b point. This one and this point is y naught minus b, and you have the rectangular region x minus, right? So you have the rectangular region which is x minus x naught a. So a lies between x naught minus a, x naught plus a. So this is the x naught minus a point and y naught plus b, and then you have this one. So you have this. So otherwise you put this is x naught plus, right? Right. Okay, so this is x naught plus a, y naught plus b. This is x naught minus a and y naught plus b, right? Now, if when you have this condition, the root lies between in this interval, right? So in this interval, now if it is other than that, if it is like this interval, then you have to look where it is it will be somewhere else inside of this x naught minus b1 x naught plus b1. Okay. Now, if for all values of x, okay. So for all values of x outside this range, so what you can comment, or all values of x, or all values of x outside whatever these two interval I gave, outside this range, if it is exists outside this range, the curve leaves the solution curve. The solution curve leaves the region R. So it is outside the region, and we cannot tell anything. Hence, nothing can be said. Nothing can be said about the existence of solution at these values. By this theorem, you can use at these. By this theorem, we cannot predict because the solutions are the solution curve is outside of this region, so we cannot tell, right? So it may be pointed out that the condition given in the theorems are so here one can point out that so the condition remark right remark so the condition in the theorem are conditions in the theorem are sufficient. What do you mean by that? Sufficient but not necessary, right? And not necessary. So that is, if the condition, that means if the conditions are violated, if the conditions are violated, the problem may have a solution, right? Sufficient means even the conditions are not satisfied, so the problem may have a solution, right? That means some other theorem you have to study for this. So let us this what I told about this we'll discuss. May have a solution. So about this, let me tell you about this. Okay. So now let me see about the example. So discuss what is that? Discuss the existence. Discuss the existence of solutions of the IVP x y dash equal to 3y. Condition is given y of 1 equal to 1 over the rectangle. I think this I have given to you earlier. X minus 1 is less than equal to 2, y minus 1 is less than equal to 4. Right? So if you look towards this, so what is our f of x comma y is 3 y by x, where x not equal to 1, y not equal to 1, so this is x naught and this is y naught, right? And in fact your a is 2, b is 4, right? Okay, so the rectangle what is So this is x naught minus 1 is less than equal to u. That means and y minus 1 less than equal to 4. So this implies minus 1 less than equal to x less than equal to 3, right? So minus 2 plus 1 minus 1 and 2 plus 1 3, and this is what is y? This is minus 4 plus 1 minus 3 less than equal to 5 less than equal to 5. Okay. So here f of x comma y is continuous right, continuous everywhere in R except, because this contains the origin, except x equal to 0. So this function f of xy 3 y by x, which is not continuous at x equal to 0. Hence you cannot tell, hence the theorem cannot be applied. Right? So the condition is highlighted as I told you, but can you tell again whether the solution exists or not, etc. Because this condition is not applied. So the theorem cannot be applied, and that is the theorem does not provide any conclusion. So that means the theorem does not provide any conclusion about the existence of solution. About existence of solution. Right? Now, so where exists a solution in R? In the domain R. So not R the real line, is the rectangular R. So however, if you solve the differential equation, right? Now if you solve these, I told you you have to solve this and then apply this condition. Now solving this differential equation, solving this, we find that y is equal to x cube is the unique solution. Because it appears one arbitrary constant, you have one condition, you can replace that particular solution is the only unique solution with respect to this initial condition. Showing that the unique solution, showing that the conditions in the theorem are sufficient but not necessary. But not necessary. Okay? But not necessary. Now we will do another example, then we will go. Okay? So this is sufficient, not necessary. Right? So the details you must work out. right? I am moving in the solution which you have done in your BSc class. Okay. So another example I will do because you are. So this is the so next is what is your IVP? Where IVP is y dash is equal to 2x square plus 3y square, y of 0 equal to 1. Okay, y of 0 equal to 1 over the rectangle, over the. So what is the rectangle? Mod x is less than 1 and y minus 1 is less than 1. Okay. So this is there. Okay. So what is your x naught here? So we are aim to find out this solution. So what is given? So you have f of x comma y is equal to 2x square plus 3y square, 2x square plus 3y square. So here x naught is 0, y naught equal to 1. Y naught equal to 1, and in fact a equal to 1 and b equal to also 1. So this is a, this is b. Here x naught was 0, here y naught is 1. Okay. So what is your r? R is, let us write that, is less than equal to 1. Y minus 1 is less than equal to 1. So that means, so it is minus 1 less than x less than 1. And then this is 0 less than y less than equal to 2. So the x, so in the rectangle, this is your domain. So now f of x y, which is equal to 2x square plus 3y square, is continuous, everywhere in R, right? Okay. In R, further, f of, if you calculate, because we need the m, so you calculate f of xy. So this is mod of 2x square plus 3y square. So I took the polynomial which is g, which is less than equal to 14. So this is your m in minus 1 less than x less than 1, 0 less than y less than 2. So the maximum is 14, right? Is 14. So therefore, at least therefore, so the function is bounded, is continuous. By theorem, at least one solution exists where exists in the interval I is equal to x minus x naught less than equal to h. So this implies I equal to x minus x naught is 0. You have to find out the h. What is h? Where h is? So find out h. Right? So what is h? So h is equal to minimum of a comma d by n. What is if your a? So a is you have 1, b is also 1, m is 14, right? So m is 14. So this is equal to then 1 by 14, right? So your interval I was x mod x less than equal to h is equal to 1 by 14. That means minus 1 by 14 is less than equal to x. So by the theorem we can tell that in this interval, right? So in this interval, at least one solution exists, right? One solution exists. Very nice. So we have applied theorem. More examples you can do in detail. Okay. So this is about existence of theorem, right? Okay. So let us go to the uniqueness part. So I think you have understood it. If you have any doubt, again we will discuss in the doubt clearing class, interaction. So let me erase that and then we will come. Existence of. So next is theorem 2. Theorem 2. So this is called sometimes Lipschitz theorem. Lipschitz Lipschitz theorem or uniqueness theorem. Fine. It is Lipschitz theorem or Uniqueness theorem. So what is given? Always, so what is given you must know. You have a given yvp, y dash is equal to f of x comma y, and y of x naught, the condition, initial condition is y of x naught is y naught. So that means the solution is known, which is constant y naught at the point x is equal to x naught. Okay. Let f of x comma y satisfy the following condition. So that is also given. Satisfy the following condition. Okay, what are the conditions? So two conditions you must have. That existence of first one, which is the f of x is continuous. Continuous at all points in the closed rectangular region, which is R is x minus x naught is less than equal to a, y naught mod is less than equal to b, where a b greater than 0, right? A b greater than 0. Then number 2 is a fx satisfied. So it is continuous. Another is fx satisfies the Lipschitz condition, right? That is Lipschitz condition on R. Sometimes we tell that, or you can tell that f of xy satisfies the is Lipschitz continuous. This is better word also. Some people tell Lipschitz continuous in Y. Okay. So it satisfies Lipschitz condition on R, namely, what is the Lipschitz condition? F of x comma y2 minus f of because it is continuous on y, so this is y2 minus f of xy1 mod is less than equal to a constant L into y2 minus y1. Either you can tell f of x comma y1 minus f of x, that is all fine because these are mod and this is also y1 minus. So where L is the Lipschitz constant, where L is the Lipschitz constant, and in fact it is positive, everything is positive, and you have this xy1 and xy2 that belongs to this closed region or rectangular region R. Okay. Then, if these two conditions satisfies, then you can tell that. Then I can erase this. Okay. So if these two conditions, one is the continuous, another is the Lipschitz condition or Lipschitz continuous. So if then these IVP, then the IVP has a unique solution, and the solution is defined, at least for all x in the interval I, which is x minus x naught, is less than equal to h, where h is minimum of a comma b by n, right? And with m is equal to nothing but, as we have told, maximum of f of xy mod, right? And xy belongs to that closed rectangular region R, right? So what it tells that if fx is continuous in R and if it satisfies the Lipschitz condition, then the IVP has a unique solution in the interval, this one where h is minimum of a comma b by m, m is the maximum of f of x comma y. So proof I think you have done. Just I will write here. If they prove, then it will take at least 3 classes, the proof of uniqueness. You can go to the book which you have done, right? Okay. So let me tell you quickly one example about this. Right? So one example which I do, because I always tell the student, this theory must be supplied with an example so that you can see how the theorem has been worked out. So let me tell about this one. Test the existence and uniqueness of the solution of the solutions of the IVP. What is the IVP? Y dash is equal to y to the power half, y of 1 is equal to 0 in the rectangle, in a suitable rectangle, you can take that. But you are in a suitable rectangle. If more than one solution exists, then find all solutions, right? So the solution is you can quickly we can do that. What is your f of xy is y to the power half, x not equal to 1, y not equal to 0 from the initial condition is this one, right? And hence by existence theorem, hence by existence theorem, hence by existence theorem, at least one solution exists. One solution exists in the interval x minus 1, x minus x naught is 1 is less than equal to h, right? So fine. So that is h you have to determine because it's suitable rectangle as given. So this is fine. Now the solution will be unique if f satisfies the solution. Now the solution will be unique if f satisfies the Lipschitz condition in R. Okay. So for that, for the Lipschitz condition, so you have to find out if f satisfies the Lipschitz condition, right? Okay. So suppose what we have f of x comma y1 belongs to R, right? Now we have what we have to show? We have to show that f of x comma y2 minus f of x comma y1 mod is less than equal to, you have to show this L into y of y2 minus y1 mod, right? So what I will do now, simply I will divide this y2 minus y1 mod here. Okay. If I show that it is less than equal to m, then f satisfies the Lipschitz condition. Then I can tell that f satisfies the Lipschitz condition. Now this is equal to y to the power half minus y1 to the power half less than whole divided by y2 minus y1. Okay. Now if you simplify that, so this is nothing but y2 to the power half minus y1 to the power half y2 minus y1. If you do this, now multiply numerator and denominator by y2 to the power half plus y1 to the power half, multiply here and here, so this you will get 1 by y2, so y to the power half plus y1 to the power half. Okay. Now this quantity, so this quantity can be made as large as possible, right? This quantity can be made as large as possible by choosing y1 and y2 sufficiently small, right? Isn't it? So if you choose very small, for example, like you have suppose y1 equal to very small epsilon that is greater than 0 and y2 also epsilon which is greater than 0, then you have 1 by y to the power half plus y1 to the power half, which is equal to 1 by 2 epsilon to the power half. This tend to infinity as epsilon goes to 0. As epsilon goes to 0. Right? As epsilon goes to 0. So that means f does not satisfy. That means f does not satisfy the Lysis condition, right? Which for any domain which contains or for any domain which contains equal to 0, right? Right? Which so which contains y equal to 0, that's fine. Hence the theorem cannot be applied to obtain the unique solution. So the theorem cannot be applied here, cannot be applied here to obtain the uniqueness conclusion, right? The uniqueness conclusion. Am I correct? So hence the failure of Lipschitz condition does not imply the. So here, as I told you, this is also a sufficient. This theorem is also a sufficient condition. Even so, it is if it is failed, the Lipschitz condition is failed. That doesn't guarantee that the IVP has a unique solution. So, however, failure of Lipschitz condition does not imply the solution is so. If the Lipschitz condition could have satisfied, at least you can tell that in that interval the solution is unique, but it is not satisfying. So you can test that. Otherwise, I will do that in tomorrow class. You can verify, and you can verify that what you have to do further. So the other consideration has to be used to examine the uniqueness, right? So of course, so you can verify that y equal to 0 is a solution, and if you solve this is right, because what is your are solutions to the IVP, to the given IVP. What is the IVP? Was y dash equal to y to the power half y of y equal to 0. So it is 0. So at any point you take, this condition will satisfies, and the derivative is also. So both sides 0, here 0. Satisfied? This is also satisfied. Hence 0 is a solution. And once you solve it, you will find out that this is also solution. So in the interval, minus infinity x less than infinity. So these are the solutions. So the problem, the IVP, hence what we can conclude that the IVP does not have unique solution. Unique solution, right? It does not have a unique solution because y equal 0 is a solution and this is a solution to the same IVP, hence it has no unique solution, right? So what we have so far seen that we'll go more some more properties, the sufficient condition again, where if the condition satisfies, then you can tell uniqueness. If the condition does not satisfy, that doesn't mean that the equation have a solution. So you have to verify it always by different conditions. The different consideration means you can always solve this. You can solve this, find out the solution, whether we can have more than one solution or always unique solution, right? That is by solving. Otherwise, you have to write the Lipschitz theorem. If the Lipschitz theorem satisfies, the condition satisfied, you can tell the existence of a solution. So here we will stop it, and then in the tomorrow class we will see some more properties related to this. Thank you very much. Thank you.